Hello guys. Today we are going to continue our discussion on R functions. And we are going to start with looking at one important aspect of function executions. That is, when a function sees a name in its body when it runs, how does it find a value for that name? Let's take a look at one example. This code snippet defines two variables, a and b, and two functions, f and g. F here is a function which takes its argument x, and it multiplies x by a, and adds the result to b. Because this expression is the last line of the function body, the R object it outputs will implicitly become the return value of this function. But a and b here are neither variables declared in the parameter list, nor something assigned within this function. Then how will R find values for these two symbols? Will F substitute these two values for A and B in the output line when F is called? F is actually called by the next function G. And the output of this call to F will further become the return value of G. And in G's body, there are two assignments preceding the call to F, creating two local variables A and B. And this pair of A and B is definitely closer to the code that makes F run. Perhaps it is more likely that R will use these two values for A and B inside F. Here the question is, if I call G with 2, what will be returned? This 2 will surely be matched to X and further passed as input to this inner function call. So X in this output line will be replaced by 2. But the question boils down to which pair of values will R substitute for A and B here? The answer is actually 4, which implies R actually associate A and B with these two values. This may come as a surprise to some of you. Actually, this example makes clear the importance of understanding name-value associations or bindings for R functions. Because otherwise we cannot estimate the behaviors of R functions and thereby use them correctly. As shown in the previous example, the names which occur in a function can be divided into 3 classes. The first kind of names are function parameters. These names are declared in the parameter list of the function. Their values are determined by the process of binding the arguments to the parameters. The second type of names are local variables. Their values are determined by the evaluation of expressions in the body of the function. And the third class of names are free variables. They are names that are neither parameters nor local variables. Their values are determined neither by matching passed-in arguments nor by evaluating inner expressions. So how does R determine values for free variables? The language mechanism that determines how a value is bound to a free variable in a function is called the scoping rules. And this is going to be the theme of the remaining portion of this unit. To introduce the scoping rules, we need to first introduce the data structure that powers scoping in R. That is, environments. The job of an environment is to associate a set of names to a set of values. So it controls how R finds the value associated with a name. We can think of an environment as a bag of names, each pointing to an object. For this reason, we can draw an environment like this. These 4 names point to their corresponding R objects and are encapsulated in an environment denoted by this shaded rectangle. An environment has another component denoted by this pale blue circle. We'll explain its meaning in minutes. Environments can be created with the new environment function. Let's first create an environment called E1 and manipulate it later. Printing an environment just displays its memory address, which is not very useful. As a data structure, an environment is similar to a named list, so we can perform many list-like operations on an environment. For example, we can get and set elements of an environment with these familiar notations as we do with a list. And in these 4 examples, we create 4 names, A, B, C, and D in E1, and associate them with their corresponding values. Alternatively, we can use an assign function to create a name-value association in an environment, and then use the get function to retrieve the value by name. In this example, the first argument specifies a name. The second argument specifies the value. And the third argument specifies the environment into which this name and value association should be inserted. Then I can use this get function to specify the name as well as the environment where we are going to look for that name. We can coerce a list to an environment using asList function. And we can also do the converse using the asEnvironment function. And there are 2 useful functions for printing an environment's content. The ls function simply prints the name's content in a given environment, while the lsstr function, which is the environment version of the structure function, prints both the meta information and the content for all elements in a given environment. Moreover, we can test if a name exists in an environment using the exists function. Because we haven't created a name called non-existing in the environment E1, so this function call returns false as output. And every name must be unique in an environment, which is equivalent to say that we cannot have different values associated with the same name in one environment. To remove names from an environment, we can use this rm function, short for remove. There are 2 ways to specify the names to be removed. The first way is to list them directly in a call, each separated with a comma. And the second way is to combine them into a vector first, and then pass the vector to the list keyword. If you want to remove all names in an environment at once, a trick you can use is to first use the ls function to retrieve all existing names and pass them to the list keyword. If an object loses all names pointing to it, it will get automatically deleted by R's garbage collector. An important aspect that makes an environment different from a named list is that every environment has a parent, which is another environment. The parent is what this blue circle denotes, and every parent has an arrow that points to another environment. This pointer component makes environments chained to form a hierarchy. And there's a special environment called the empty environment that doesn't have a parent and thereby serve as a root of this hierarchy. We've seen how to use the new environment function to create environments. Actually, the new environment function has a parent parameter, which allows us to specify the parent for the environment we wish to create. Here, we create a new environment named E2A, which is a child of the empty environment. This function is used to retrieve the empty environment. Then, E2A is used as the parent to create another new environment, E2B. So the hierarchy among E2B, E2A, and the empty environment is depicted by this diagram. The parent of an environment can be accessed with the parent environment function. And if we call this parent environment function with E2A, you can see the empty environment is printed as a special string. In addition to the empty environment, there are three other special environments in R. The first special environment is a global environment, also called the workspace. The global environment is where all interactive computation takes place. All variables and functions you create in your console actually exist in this environment. The global environment can be accessed with this function and printed as either of these two special strings. The second special environment is a base environment. It is the environment for the base package. We've talked about the base package briefly in the course introduction. Let me refresh your memory on it. The base package is a package that provides all fundamental functions we need to run the R system, and it is automatically loaded when an R session starts. The base environment can be accessed with this function, and its parent is an empty environment. And the environment in which code is currently running is called the current environment. And it can be accessed by calling the environment function without arguments provided. The environment printed here is the environment used to render these slides. If you run this code in your console, it will instead print the global environment, which means that your code is currently running in the global environment. In R, most environments are not created with the new environment function as we did previously, but are created as a consequence of using functions. There are several important environments associated with a function. The enclosing environment is the environment where the function is defined. It is this environment that determines how the function finds values, as we will see shortly. When calling the environment function with a function object, it will return the enclosing environment of this function. As you can see here, the enclosing environment of this simple function is just the current environment, because it is defined within it. And each time a function is called, a new environment is created to host its execution. This environment is called the execution environment. Here I use another version of the simple function to illustrate the execution environment. The function body includes two assignments that create local variables: a print function call that prints the current environment when the body is being executed. And finally, a call to the environment version of the structure function to list its content. As you can see, when it is called with the argument 2, a new environment is created. And this new environment is populated with both the parameter variable x and the two local variables a and b. The execution environment is normally ephemeral and disappears after the function returns a value. And every execution environment is associated with a calling environment. It is the environment from which the function was called. Relating this back to our motivating example, we can find the execution environment of G is a calling environment of F, since function F is called within the body of function G. And applying the concepts we just learned, you can find that because function F is defined in the current environment, its enclosing environment is the current environment. Remember, what we are discussing is that how does R determine values for free variables A and B? And we have two sets of A and B defined in F's enclosing environment and calling environment, respectively. So a more specific question is that if no name binding is found in its execution environment, whether function F will find them in its enclosing environment or in its calling environment. And how are these different types of environments are related to R scoping rules? Actually, R relies on the hierarchy among these function environments to find values for free variables. It walks up the chain of environments and uses the first binding for a name it finds. In simpler terms, if a name is not found in an environment, then R will look in its parent. If the name is still not found in its parent, R will look in its parent's parent, and so on. In R, the parent of a function's execution environment is its enclosing environment, as opposed to its calling environment. So the values of free variables are searched for in the environment in which the function is defined. Because the search for name value bindings depends on the code's static structure, rather than the dynamic relationship manifested through the code execution, our scoping rule is called the lexical scoping or static scoping. In R, functions are objects in their own right. Moreover, they are first-class objects. In a programming language, a first-class entity is an entity that supports all the operations generally available to other entities. So by first class, we mean that function objects in R can be computed, parsed, stored, and returned wherever other objects can be computed, parsed, stored, and returned. For example, as it can return different data objects, an R function is also able to return another function as its return value. In this example, the last line of the body of function f is a function definition, which evaluates to a function object. So this anonymous function implicitly becomes the return value of a call to function f. Here we call function f with the arguments 2 and 1, and it returns a new function, which we assign it a name g. If you type g in your console, it prints this, confirming that this name g is referencing a function object. And we can further call function g with an argument to x. And it generates the output 5. But then you may wonder how this returned function finds the values for a and b when it is called with 2. Because this anonymous function is created when executing the body of function f, its enclosing environment is the environment that hosts the execution session initiated by this specific call. And in this call, the arguments 2 and 1 are passed in and match these parameters a and b. So there are two variables called a and b existing in this specific execution environment. And this execution environment is bound to the returned function even after this call terminates. And in this case, the execution environment is no longer ephemeral or transient. And all functions in R remember the environment where they are created because they need to refer to them for value bindings for free variables. There's a specific term that refers to the combination of a function and its enclosing environment. That is a function closure or closure. Here, let me revise the previous code for function f a bit and include a print line that prints its execution environment whenever it is called. So when we call it with the arguments 2 and 1, again, it can print the execution environment initiated by this call. Once we call the environment function to retrieve g's enclosing environment, you can find it is exactly the same as the execution environment initiated by this call. Now, it should be clearer to you that the execution environment is bound to the returned object and does not disappear after this call. If you apply this environment version of the structure function to g's enclosing environment, what you can find is that it bundles values for a and b and provides name value bindings for g's free variables. Function closures have many important applications. One of them is function factories, which are functions that can make new functions. The example here is this power function, which outputs an anonymous function as its return value. And here, I call it twice with different arguments to the parameter exponent, resulting in two functions. We name them square and cube. So these two functions are associated with different enclosing environments, which result from running the body of function power at different times. And these two enclosing environments provide different value bindings for the free variable exponent. Please try to call them with 10 respectively in your console. Now you should be able to see how we can use a function factory to manufacture different functions for computing powers with different exponents. Next, I would like to introduce a useful tool that is relevant to function environments and allows us to make our customer functions more versatile. In this example, A included on the right-hand side of this assignment is a free variable. And thanks to the scoping rule, F can find a value in its enclosing environment for this A. Then this assignment creates another A in the current execution environment to reference the output of this addition. In the end, this A is returned as the output. Then the question is there any change made to this A? The answer is no, because the change we made only matters to this local and transient A. So attempting to modify an existing variable from within a function is in vain with this regular assignment operator. But R actually provides a super or deep assignment operator denoted by this notation, which allows us to modify an existing variable found by working up the chain of environments. So if we change the regular assignment to this deep assignment in the body of function g, then what gets modified by this assignment is this existing variable in the enclosing environment of function g. And this can be verified by type A again. As you can see, the content has been modified. But if instead you try to modify a non-existing variable with the deep assignment operator, the assignment will then result in the creation of a new variable in the global environment. I will spend the last several minutes of this video introducing another type of environments, that is, package environments. If you run the search command in your console, R will return a list of strings, most of them prefixed with the term package. They actually correspond to the package that were automatically loaded when the current R session started. R created an environment for each loaded package to contain every publicly accessible name defined in that package. So each entry prefixed with package in this list represents a package environment. You can print all names contained in a specific package environment using this type of code. Try this code in your console. The order in which these environments are listed actually matters. They make up the search path that R works up to find the first binding for a name. You may have wondered where R finds the functions for these names. The search path is actually the answer. As introduced earlier, the global environment or the workspace is an environment for interactive computing and contains all names you create in your console. It is actually at the top of the chain of environments in the search path, meaning that it is searched first. If a name cannot be found in the global environment, R walks up through the chain and eventually finds the name SD in the stats package environment, and min and sum in the base package environment. Each time a new package is attached with library, it is inserted between the global environment and the package that was previously at the top of the search path. In other words, it becomes the immediate parent of the global environment. Here I use the library function to attach this tidyr package to the search path. And as you can see, it is inserted between the global environment and this neatir package environment. In addition to attaching a library, we can also use the attach function to slot an object into the search path. This creates an environment which is populated with the names contained in this object. Here I create a list called Z, which has two named components, and then attach it to the search path. And a new environment named Z is inserted just above the global environment. Then the names mean and median become searchable by R, as shown here. Actually, we've come across the attach function before. Recall that by attaching a data frame to the search path, we can refer to the variables in the data frame by their names alone, so as to avoid tedious indexing. And you should remember to detach these objects after use. Otherwise, there could be too many names in the search path, and they potentially lead to name conflicts. R is intelligent enough to distinguish functions from non-functions. The name mean in the environment Z won't mask the same name function in the base package. But if you accidentally create a function named mean in your console, then the base mean function is gonna be masked, as shown by this example. Then you can either use this double colon notation to specify the package from where you want to look for the mean function, or remove this name from the current environment to address name conflicts. That's all for R functions, and we'll start a new topic on the family of loop functions in R next time.